Sometimes science models are completely useless, other times they are wonderful. But would you trust this fella to go where he's predicted? I've been watching the path of Cyclone Jasper because it's just off the coast here, and it reminds me of how some model predictions are completely brilliant, some are broken, and most are probably somewhere in between. Now, weather forecasters are often unfairly criticised for getting their predictions wrong, but they do often get them wrong. In other areas of science, predictions are phenomenally accurate. So, for example, the eclipse that occurred on the 14th of October this year was perfectly predicted. And scientists have known for a long time how to predict them. So, for example, in 1769, Captain Cook was sent all the way from England to Tahiti to observe an eclipse. Today, there's even a website which will tell you the timing of all the eclipses for the next 100 years. So, for example, there's going to be an eclipse at 1657 on the 14th of September 2099, and it will last for 5 minutes and 18 seconds. What a wonderful prediction, and I bet you it will be right. I wonder what the weather will be like at 1657. Well, you may as well toss a coin. So why are some predictions so brilliantly accurate and some pretty ordinary? For these examples, it boils down to a few things. Firstly, do we perfectly understand all the physics or chemistry? And how much error do we start to accumulate the further the predictions go out into the future? To predict where the planets and the sun will be, it is not much of a stretch to say that all we need to know is Newton's laws of motion and his law of gravitation, which we know very accurately. It relates the gravitational force to the masses and the distances between the objects. And the constant in the equation, this gm, we know very accurately, an error of only 1 part in 10 billion. Nice and simple physics, very accurately known constants. Now, for weather and for climate predictions, much more tricky. The models that meteorologists run solve a bunch of equations which include Newton's laws of motion and the laws of thermodynamics and many more. And some of these processes are extremely well understood, but others, well, actually we have very little idea about. So, for example, the cloud physics is a huge hole in our understanding, but it is fundamental to how a lot of the weather works. So what do you do in your model when you don't understand some particular process? Now, as a person who's done a lot of modelling of physical processes and a different range of things, I can tell you what you do. You just got to do the best you can, and you might be able to make some sort of statistical relation, which usually requires a bit or maybe a fair bit of guesswork. And that's where inevitable error comes in. But then there is another problem for weather forecasters. Some of the physics is what we call nonlinear. Now, this has a very precise meaning in mathematics, but basically for weather it means that the further ahead one wants to predict, the error just explodes very, very quickly. Now, this is especially the case for predictions of fluid and air, i.e. in the atmosphere. How do you fancy predicting where a water particle would be minutes or an hour ahead in the turbulence at the bottom of this plunge pool at the bottom of a waterfall? But the physics that describes it is almost exactly described by Newton's laws of motion, just like the eclipse. But this case is so hopelessly non-linear that you just can't make a prediction. The third problem for weather is that to make a prediction, you need to know what the weather is everywhere right now, not just on the ground, but at every layer of the atmosphere. For predicting an eclipse, you just need to know exactly where the moon, the sun, and the earth are right now, and that is way easier than knowing the temperature, the humidity, the pressure, and the wind speed for the whole atmosphere all the way around the earth. I mean, for the moon, the sun, and the earth, it's just their position and the speed. For the weather, you need to know the conditions in a million places. And if you get that initial condition wrong with these big systems of fluids, then your prediction just goes to pieces extremely quickly. Now, give the weatherman a break. The predictions are getting better and better, especially for cyclones. In fact, one reason they're getting better is not the understanding of the physics, the equations, so much as the way that the satellites can now measure the initial conditions much better. 20 or 30 years ago, it was very hard to measure mid-atmospheric temperatures. It's now done completely routinely. So predictions of eclipses are brilliant science. Does that make the weather predictions broken because they're not so good? Well, no, absolutely not. The weather predictions are actually quite wonderful. You just mustn't push them too far out into the future. That's when they become broken. So for example, for Cyclone Jasper, right at the beginning, well, the models were pretty ordinary, giving totally different predictions. They probably should have, under those circumstances, just said, well, the prediction is we have no idea. Now, saying we can't predict it doesn't sound like brilliant science, but it's way better than making a prediction when it is known to be hopeless, or when there's been no due diligence to test whether the prediction is useful. That is surely broken science. Think some of the climate models, and think some of the COVID models. Maybe that's something for a future episode. So what do you reckon? How many marks out of 10 do you give the weatherman in your area? I'm going to give him 8 out of 10, but if that cyclone does a dogleg and comes back this way unexpectedly, well, I might change my mind. Well, I want to update that score. I gave them 8 out of 10 before. Well, they said a few days ago it was going to go up a bit north of Port Douglas, and that's exactly what it did. So I think 9.5 out of 10, maybe even 10 out of 10. Why not be generous? How much better can you get after all?